Hey guys, welcome to our lesson 10.1 parabolas. Now we've all dealt with parabolas before and we've seen them in various different functions or various different situations, right? But they all always came from a quadratic function, right? Something like y equals ax squared plus bx plus c. Now this gave us a very specific type of parabola depending on where it was centered, where the vertex was, and how kind of wide or narrow it was. But in general, right, we've dealt with these kind of parabolas. The terrible other side. That's still bad, but all right. But a parabola is just this kind of shape of a graph. It does not necessarily mean a function in the traditional sense that we think about. But so we want to be able to talk about parabolas that go other directions, say this way. And the way we're going to do that is we're going to talk about them in a little different manner. And so what we want to do is we want to build up some verbiage, some vocabulary to help us talk about different aspects and features of a parabola. Right? A parabola still has a vertex and an axis of symmetry. We're going to talk more about some other things. A focus and a directrix are going to be two terms that we're going to bring up that we're going to talk about here. So let's first get this first definition. So very simply, a parabola is simply defined to be a set of points that are equidistant from a fixed point and a fixed line. The fixed point is called the focus, and then the fixed line is called the directrix. Okay, so I'm going to give you kind of a visual of what that means, kind of how that looks. So if we have here our focus, okay, and then let's say that this point here, or this, let's go, this right here is our directrix. So this is the focus directrix. A parabola would be something like this. And what's really cool here is for any given point, now this is obviously, ignore my terrible drawing. But these distances, let's call this one here D1, this is D2, D1 is equal to D2. For any point, kind of the distance from the focus and the distance from the directrix are equivalent. Again, ignore my terrible non-to-scale drawing, but that is kind of how this idea of a parabola built off of a focus and a directrix work. And so what's really nice about that is we can see here that that the distance between the directrix and the focus, if we cut that in half, that is where our vertex is. Okay. So we'll talk about how to find that and stuff like that. So let's talk about the general equation. So there's two general equations, and it all depends on whether the axis of symmetry is a vertical or a horizontal axis of symmetry. So a traditional parabola that we've dealt with, the y equals ax squared plus bx plus c, that would be a vertical axis of symmetry. Okay, so what that means, or a vertical axis, what that simply means is that our axis of symmetry goes up and down. And so that equation, the general equation of that, looks like x squared equals 4py. And we're going to talk about how to move these around and slide them and stuff like that using translations in a little bit. But so given this general equation, our focus will be at the point 0, p. Our directrix is the line y equals negative p. Our vertex is at 0, 0. And our axis of symmetry is the vertical line x equals 0. Okay. So what this gives us is it gives us a very simple function or a very simple graph of kind of a more traditional parabola where this is the focus. Let me kind of try and get a nice little dotted line here. This is the directrix. This distance here is P, and this distance here is P. So what's really cool is based on this, we can kind of figure a lot of things out with these functions. Okay. So now let's talk about a horizontal axis, and then we're going to kind of come down and talk about these a little bit further. So if you really just kind of simply flip these variables, we get our horizontal axis, because that's really what's happening is we're flipping this graph from going along the y-axis, so kind of going opening up or opening down to opening left or opening right. And so our equation very simply flips, and we get the equation ugly y squared equals 4px. Now our focus isn't going to be at 0p because that would be having a y value be the p. So our focus here is it's flipped is p comma 0. Our directrix, instead of being y equals negative p, it's simply the line x equals negative p. Our vertex is still going to be at 0, 0. Our axis of symmetry is going to be y equals 0. So here, this would be a graph kind of in general opening sort of like this. Okay, with our focus here, our focus. And this being the directrix. Again, these distances are p. And so that's really kind of a nice, very, very basic, simple way. So if you would kind of imagine back into, so like the vertical axis here, this would be like y equals x squared. Kind of helps us out with that. Okay. So now what's really cool is we can kind of identify these. So if we identify whether or not we're dealing with a vertical axis of symmetry or horizontal axis of symmetry, which from the equation really comes with which variable is being squared. Whichever variable is being squared, so in this vertical axis version, x is the variable being squared. So whatever variable is being squared, so that is the x is on the horizontal axis, it's the opposite. Okay, so since x is being squared, it is going to have a vertical axis of symmetry. And our other one, since y is being squared, that y's are graphed on the vertical axis. That tells me that this is a horizontal axis parabola. And so once we have identified whether it's vertical or horizontal, then we can look at the p-value, see if it's positive or negative, and that tells us whether it opens up, down, or left, right. And if p is positive, and we're dealing with a vertical axis symmetry, okay, then we open up. If p is negative, we open down. Now, if we're dealing with a horizontal axis of symmetry, and p is positive, it opens to the right. And if it's negative, it opens to the left. And what's really nice and easy about this is that p-value, just think about this, is once you know which axes you're looking at, whether it's in this case here with on the left side, we've got vertical, on the right side, we've got horizontal. P is positive. Well, on the vertical axis, the positive values are up, the negative values are down. So if p is positive, it opens up, p is negative, it opens down. Similarly, with a horizontal axis, a parabola, the positive values are on the right side and the negative values on the left. So if p is positive, it's opening to the right. If p is negative, it's opening to the left. And so right now we can kind of get some nice information and help with this. But these were all very simple functions that have their vertex at the origin, or sorry, very simple parabolas that have their vertex at the origin. But we know that's a very limited set of functions or set of parabolas. So I want to expand these to get some general forms of these parabolas that open up from other areas that have their vertex not at the origin. And so what we're doing here is we're just very simply doing some vertical and horizontal translation, some shifts. And so in our general equation of a vertical axis, okay, it's going to look like x minus h squared equals 4 times p times y minus k. Notice that x minus h and that y minus k quantity are in parentheses. And the reason for that is because we want to exactly subtract h off of k to shift our graph and subtract k off of y to shift our graph. And those just give us our movements. Now, what this does for us is we now have to adjust our focus, directrix, and vertex and axis of symmetry based on these shifts of h and k. And so if we go back up here to what we had, okay, our focus was at 0p. So what's going to happen now, because what's happened is we've moved h units in the horizontal direction and k units in the vertical direction, our focus that was at 0p is now going to be at h, comma, k plus p. Draw a different k. Stick with the same k. And so if you think about that, we took the point 0p and we moved it h units horizontally and k units vertically. So it changed to h, k, comma, k plus p. Our directrix used to be the line y equals negative p. Now it's going to be the line y equals k minus p. Essentially, we're just adding k to it. Now our vertex here was at 0, 0. We've moved h units horizontally, k units vertically, so our vertex is now at hk. Our symmetry was the line x equals 0, so now it's going to be the line x equals h. Right? What's really nice is the axis of symmetry always goes through the vertex, right? So if our x value of our vertex is h, then our axis of symmetry is going to be x equals h. Okay. And now what that looks like could be something like this. Okay. Where this distance here is p. This distance here is p. This point is the point h comma k. Right? This point here is the point h comma k plus p. This line is the line y equals k minus p. Okay, and so we can kind of see how this starts to kind of fit together. And we can do an exactly similar thing for horizontal axis parabolas. Now, remember, the difference between a vertical and a horizontal axis is we're just basically flipping our variables. And so our equation in general for a horizontal axis is simply y minus k squared is 4px minus h. Now we're keeping the x, the h, and the k with the x and y respectively, mostly just to not make things complicated. Okay, and our focus, instead of being the point p comma 0, is now h plus p comma k. Our directrix, instead of being k minus or x equals negative p, now x equals h minus p. And our vertex is hk still. Our axis of symmetry is now the line y. Instead of y equals 0, it's y equals k. In our graph of this, again, these distances here are p and p. Our vertex, again, is still at the point h comma k. This point here is at the point h plus p comma k. And our vertex here is at the now, or sorry, our directrix is now the line x equals h minus p. Again, depending on our p-value, it's still the exact same. If p is positive, it opens up. P is negative, it opens down. If p is positive and we're opening horizontally, right, we have a horizontal axis, then it's still opening to the right and then still opening to the left. Okay. So this first set is good to know, right? It's kind of the more simple version. But this is the point. This is this kind of general equation we're really going to use. Now, what I want you to think about is how does the p-value affect the opening of the graph? So we'll get into this in a little bit, and we'll do some examples and stuff like that. And we'll kind of see how some things work and see how some things change. But think about this: is as p gets bigger, let's just stick with a very simple one. Is our function, is our graph going to become more narrow, or is it going to kind of widen out? Right? So that distance between P and, or sorry, the focus and the directrix is what's changing here, right? Based on this P value. So what we have to think to ourselves is, how can I kind of think about this visually? So what we're looking at is the distance from this, say this is our focus, which means this value here is P. Okay, we have a similar distance. And here, if we kind of have a similar p-value, right? Notice that doesn't work. Right? Granted, my drawings are not perfectly to scale or anything like that, but we can clearly see that if these have a roughly equivalent p for the focus, this distance for a narrow one is very small, whereas the distance for this larger one is very big. So that means this p is smaller, this p is larger. Okay. So the bigger the p-value is, the more wide our parabolas are. Okay. So that's kind of a nice thing to know. So we can kind of look at a graph, look at something and be like, cool, once I identify its p-value, I can kind of go through and figure out, okay, is this going to be really wide? Is it going to be really narrow? And right, the difference from like say 3 to 5 isn't going to really care. We know that the p-value of 5 is going to be wider. But if you say my p-value is 1 or 100, right, the 1 is going to be pretty normal. The 100 is going to be pretty wide, right? And if we say p is 0.01, we know it's going to be really narrow. So let's look at this first example. We need to find the vertex, the focus, the directrix, and then give a rough sketch. Now, before we do any of this, it's really nice and helpful to identify if we are dealing with a vertical or horizontal axis. So we have y squared equals negative 10x. So if we look up here, okay, that would give us something with a horizontal because this has our y component being squared. So we are dealing, this is giving us a horizontal axis parabola. So I'll write that out so we have it in our notes. So since y is squared, we have a horizontal axis parabola. Okay, so now let's find the vertex, focus, and the directrix. Okay. Now to do this, we need to identify P. Now this doesn't have any shifting left or right. right? We can see that. So our vertex is really easy here. Our vertex is going to be at 0, 0. Because y is being squared by itself, there's nothing happening extra there. And x is just by itself, right? It's multiplied by the negative 10, but that's our 4p. We don't have x minus 3 or anything like that. So because of that, we know that we can simply say that our vertex is at the point 0, 0. So now what we have to try and find is our focus and our directrix. Once we know once we know our p-value, this becomes really simple. So we know that the kind of general equation we're dealing with here is y squared equals 4px. Well, what we're actually given is y squared equals negative 10x. So that tells me that 4p equals negative 10. So I'm going to divide both sides by 4 to tell me that p is negative 5 halves. And we want to leave it at that, right? We don't want to change this to be a decimal, right? I know a lot of you guys are champing at the bit, like, oh, decimals, please, not fractions. But we're mathematicians here. We're going to keep this as a fraction because that's better to work with. So if we go all the way up, we could look at this one here, but because we don't have any shifting, we can actually simplify our lives and look at this. Since we have a horizontal axis parabola with our p-value being this negative 5 halves, our focus is at the point p comma 0, and our directrix is x equals negative p. So if we just come back down to our example, our focus is going to simply be at the point negative 5 halves, comma 0, and our directrix is the line x equals negative p. So negative 5 halves is just positive 5 halves. All right. So we know our focus, we know our directrix. Now, real quick, we're dealing with horizontal axis parabola, right? So this is either opening left or right. Our p-value is negative 5 halves. So before I do anything, is this going to open to the left or is it going to open to the right? Good. Hopefully you guys said to the left, right? Because on our horizontal axis, I'm going to move over here so I have a little more room. The negative values, so since p is negative, the negative values are over here to the left. I said right earlier. Left is what I meant. Left. This opens to the left. My bad. So it opens to the left. So right about here is negative 5 halves. And right about here is positive 5 halves. So this is our directrix here. And this is our focus. We know our vertex is here. And now, while it'd be really nice to kind of, have something that would measure this out, we're just going to, sketch a parabola. All right. And there we go. There we have it. Now, for those of you wondering how are we going to graph these things later, say like using our calculator, hold off, and I promise we will talk about that. So let's move down to our next example. Find the equation of the parabola with a vertex 0, 0, that's nice, and focus 0, negative 10, then give a rough sketch. So I'm looking at this and I see vertex of 0, 0. So I know we're dealing with those kind of first two function sets, not our kind of second more general shifted versions. So I know this is either going to be x squared equals 4py or y squared equals 4px. Now, without going all the way back up to the top, I can just look at our last example, because our last example also had a vertex of 0, 0. So our focus here is 0, negative 10. In our last example that opened horizontally was negative 5 halves comma 0. Notice those are flipped. 0 is in the opposite spot. So that tells me that this is going to open vertically. So this is going to have a vertical axis. And in a vertical axis, okay, our focus is at the point 0, comma, p. And since our focus here is 0, negative 10, tells me that p equals negative 10. So that means since it's a vertical axis, our graph is going to be x squared equals 4 times negative 10 times y. Or if we want to be nice and simple, x squared equals negative 40y. Now, if you're wondering how to graph this is really easy, right? To graph this in our calculator, just solve for y, and we end up with y equals x squared over negative 40. Punch that in your calculator, graph it, and there you have it. So, is this going to open up or down? All right, well, we know our vertex is at 0, 0, and our focus is at 0, negative 10. So is this going to open up or down? Well, remember, we just have to say, okay, we know this is opening up or down. P is negative. Negative values are down, so this opens